Hey, Hannah, thank you so much, and welcome everybody. This is our fourth installment of the Incubate Energy Labs Lunch and Learn series. My name is Annie Haas, and I'm the program co-lead at EPRI in our Technology Innovation Group. I'm really glad you're all here today. These projects are so much fun, and we started this series to really highlight some of the stories that are coming out of these demonstrations. They're all accelerated. We did 10 projects last year, and the goal is to connect utilities and startups and the R&D expertise at EPRI to really kind of work on a collaborative, accelerated demonstration to really test some new things and see how well they scale in a utility environment. So today's company, PingThings, brings forward a really cool platform for data management, and data is such a big issue with all of the projects that we run. We have so much of it, and we got to figure out how to manipulate it, how to safely and securely store it, how to use it to our benefit in the utility industry and more. So Ameren stepped up last year and said, you know, we'd like to do a demonstration with PingThings. So Ameren led this demonstration. We had a number of other utilities following along the way, Con Edison being one. And then we, of course, had a great subject matter expert from EPRI, Ed Barasett, who you may hear from today to kind of help guide the R&D portion of it to make sure that in this demonstration we were tackling and answering some outstanding research questions. So before I pass it over to PingThings CEO, Sean Murphy, I just wanted to do a quick plug for our next two Lunch and Learns. Our April Lunch and Learn will feature Recurve, and that is from 1 to 2 Eastern on April 16th. And then our May Lunch and Learn will feature EV Energy, and that is from 1 to 2 Eastern on May 21st. So be on the lookout in your email inbox. Feel free to PM me either on this call or after the fact if you want more information. But I think that's all what I wanted to say to open this up. So without further ado, please welcome Sean Murphy, the CEO of PingThings. And Sean, the floor is yours.
With that type of introduction, I now expect applause and maybe some theme music for the, from the late night show. Thank you. I appreciate the opportunity to talk and to hopefully entertain everyone here as you eat a late or central lunch. And really, actually, that's the first thing I wanted to start with is to thank you for showing up. We're very excited about our company, our platform, what we can do with sensor data. And we were excited for this opportunity to work with Ameren, and we're very glad to be here. So this is what we're going for today. I'm going to do some quick intros. I'm going to overview the project, and then we have some folks from Ameren, particularly Scott Hickson in the audience, so he might add a little color to the project overview as well. And then next, going to talk about the platform, the PingThings Predictive Grid platform. It's our time series data management, analytics, and AI platform, and give you some short demos to show the other things that we do before I'm going to hand it over to Chris Ryan for a technical deep dive and possibly some live coding. That's always dangerous. Stuff always goes wrong, but we're probably going to give it a try and really talk about some of the algorithms and some of the approaches used. Then talk about some conclusions and open the floor up to questions. So in terms of introductions, got to start with really the Ameren team, including Scott Hickson, highlighted with that red box. A wonderful team, really a pleasure to work with, and a very diverse team, because we worked with folks who were interns, we worked with folks who were full-time from different groups, et cetera. Just a very positive experience collaborating. So I just wanted to say thank you, and to know that a lot of this work that is being presented was made possible. This was a collaborative effort. And as I talk a little bit about the project, you'll see that really shining through. Now, note the PingThings team was a bit smaller, and this is also the speaking team today. So I'm Sean, I'm the CEO, and as a quick intro, I actually was biomedical engineering senior scientist at Hopkins for a number of years before switching over and throwing on the entrepreneurial hat. And so time series data has been near and dear to my heart for quite some time. And then Dr. Chris Ryan will be doing the technical deep dive. I managed to snag Chris from another company. He has a rich and robust background in data, both in a commercial, like actually getting stuff done, and an academic sense as well. He has a PhD, and he was working on a lot of protein folding. So we're talking high performance computing, which is great. And not on this slide, we had some Devin help from Alan, who's leading up our infrastructure team. As a quick overview for the company, PingThings really went to market in 2017. 2020 was, we tripled in size. We went from 5 to 15 full-time employees, and we're expecting to at least double to 30 this year. And we're doing this kind of the old-fashioned way. We're a seed stage funded company, and we're growing through revenue. I know it's novel in Silicon Valley to do stuff like that, but that's how we're doing it. And we have customers from energy, including transmission and distribution, but then also in telecom and transportation. So our platform is being used to process large volumes of time series data for a number of verticals. Now, just as a quick thing, the platform that we use, and one of the reasons why PingThings exists, is because we've had strong backing from the government, and that's really based on the strength of the platform that's formed the core of all of the grants that we've received. And all of these grants are still ongoing, and but I won't be talking about those today. So as a project overview, the opportunity last year through EPRI and with Ameren was really an opportunity to stretch and to demonstrate for the rest of the industry that our platform wasn't just a synchrophaser data platform. So what Ameren wanted to do is they had terabytes, single digit, but still terabytes of smart meter data. I want to say this was about 1 million meters. Each meter had several data streams attached to it, and we had about a year of data. So this isn't enormous data. This isn't Google scale. This is a nice test case. It's big enough to be meaningful, but it's not, it's not something where setup is going to take years. So Ameren has 8 terabytes of AMI data, and what they need to get done is something that actually I learned was a problem, and that is the grid topology on the distribution side is known. However, there is some question as things evolve, as things get fixed, as things occasionally get rewired or reattached. Connections change. So which transformer a smart meter is connected to, it may change over time, and therefore the official record might not get updated, or the official which phase this meter is on might not get updated. So there is a base of information, but it is not 100% accurate. So what they wanted to do was to take the smart meter data, and they wanted to use that information, a year of these measurements, to infer grid topology and understand which phase a particular meter was on. And there are a number of published approaches to doing this. And as we all know, a publication does not mean an operational algorithm or approach, but it means an idea. And our goal was to take these algorithms that had been documented in publications and really implement them and try to help Ameren get better information about their connectivity, how smart meters were connected to the grid, and which phase they were on, which I think is a fantastic, I don't want to call it bite-sized, but it's a defined problem. And it is a really nice, I don't know, it's a really nice short-term project, which I think they did a wonderful job defining. And this is where it gets really fascinating, because what they wanted to do was they wanted to take AWS and services offered within AWS. So services like Amazon S3 and others, and they wanted to build their own sort of solution. They wanted to implement the algorithms on their own using AWS tools. And then they were going to compare that across a number of different benchmarks and metrics to doing the same thing with PingThings, the PingThings predictive grid platform. And this is great. This is exactly what we want to do. We think we're better. I'm opinionated and biased. And then just as a quick project timeline, there was a snafu at the beginning to gain access to the data, which despite the obstacles, I thought the team adapted, came up with an approach, and we got the data and just kind of time shifted the project. But this sequence of steps, us standing up the platform, ingesting the data, assessing the quality of the data, and then prototyping the analytics, and then iterating on the prototypes to scale them to a larger data set size. It's pretty standard. And this is it gives you kind of an overview of how these projects run. And then of course, working on final reporting. I'm going to pause. Any questions? I hear silence. Maybe everyone's eating.
Hey, Sean, I'd anticipate we'd probably have a lot at the end. So why don't you go ahead and
I'll just keep moving then.
Yep, there you go.
Okay, so the whole punchline for this was, Amarin's going to use a predictive grid platform. And what that is it's a time series data platform, and it's for data management, it's for data analysis, and it's for the application of machine learning. And we like to think that it's very fast and it's very scalable, and it's also cost effective. So I'm going to talk to you a little bit about the platform now. And this was the platform used in the project. So for those of you with a technical bent, this is our system diagram. And I'm going to go through it quickly, kind of piece by piece. So on the left, we have data sources, and we will take sensor data, streaming or ETL uploads, however people want to get them to us. We don't care. We support lots of major formats, and if we don't support a format, we will. In this case, we actually had to develop ingesters for the AMI data that was exported for us by Amarin. But we can also handle ETL of metadata if there's tags and other information, geospatial data, and also network topology. Those were not utilized in this project, given its time span. But all of the time series data goes into our highly scalable time series database. It's very fast. It's one of the important things. And we have a number of other capabilities, including a signal processing at scale framework to apply time series data transformations to the data. We support user-defined functions that trigger on events. And this project, which used Jupyter Hub for literate computing and programming methodologies. But then we also have optional managed services where we will connect up in a Spark cluster or TensorFlow cluster or Array cluster. And in this project, we actually played around with the Array cluster for general compute. Now, at the front of all of this is our API and access control layer, which allows basically applications and other, basically data can come out of the platform and drive different applications and analytics and use cases. The platform comes with a number of those, and then our customers are building some other ones. And we like to think of ourselves as a horizontal layer as opposed to another silo within the utility. And again, we built this for scale. So this entire thing is a distributed computing system. we don't want to run on one server. We run on a number of servers, and we can scale out to a large number of servers. So, and all of that infrastructure, all of that behind the scenes it just runs, it just works. So, you know, our customers don't have to worry about that. We do use a new data structure for time series data. And I bring this up because my inner computer science nerd wants to tell you, but also because we support a number of things that I think are very important, like dynamic sample rates for adaptive sensing, out of order insertion if you have a comms dropout and data gets cached locally, but it doesn't get sent to our platform. We can easily accept that data a day or 2 days or a week or a year late and insert it out of order without any type of performance penalty. And we also version data, which is really interesting for data governance, data provenance, auditable analytics trails, lots of various uses for that as well. It's awesome. And that kind of brings me, this is the one Selfpity Slide, which is we're really fast, we're really scalable, and we're very cost effective. And that's based on our technology. There's one salesperson here, and that's me. And you know, I have multiple science degrees. It's really, our technology is why the company exists and why we're successful. Our largest customer is in, you know, the hundreds of terabytes, fractions of a petabyte. We can ingest and read and write data that scales linearly, so we can keep adding nodes for better and better performance. And we pretty much trash everything that we've seen that's out there, and then we do this cost effectively with a number of technologies. Yeah, we can deploy pretty much anywhere, but do prefer the cloud. I'm going to skip over this because I think this was really the heart of the project, really the comparison between build it yourself and having an out-of-the-box solution that works, that it still allows some customization. Okay, so they say show, don't tell. So here is a quick, let's make sure this is, hopefully the video comes across the screen. This is our web-based application for data exploration. We're searching through hundreds of thousands of time series data. And this is actually synchrophaser data. And what we just loaded basically instantaneously was many data points, over 1 billion. And now what the user is doing is just zooming in and out, engaging with the data, exploring it because they saw an anomaly, something of interest. And now what they're doing is they're zooming into this is DFR data, this is point on wave. I don't know the frequency, it's probably around 5 kilohertz. But as you can see, all of the interaction is just, this is a web app, nothing special. And this is a web app connected to the platform over a VPN. So the performance you see, it's not sped up, it's not, I don't know, frames aren't being dropped. We built something very quick. And now what we're doing is we're zooming back out to gain perspective on where we were in the time series. And then we're going to switch over and we're going to actually use the geospatial interface for a brief moment. And that'll happen in a second. There we go. And this is actual utility data that has been anonymized. So the lat long, the names, etc., they've been fully anonymized and accepted, okayed by the utility in question. And again, this is just giving you a sense for, hey, wow, this platform is really fast, and it allows you, the user, to have a very easy, effortless. You can engage with the data, which is what we wanted. I'm going to stop this, and I'm going to show one more demo. Okay, actually, these are some of the transmission PMU use cases that have been implemented on the system. A whole ton, a bucket full, if you will. But But this is actually interesting because this is from the distribution side. I'm not sure if you're going to be able to hear the audio. This is a project deploying, potentially deploying continuous point on wave at 10 kilohertz on the distribution side. And can you hear the audio? So we can see how well they match each other.
It's not coming through very clearly.
Okay, that's fine. I'll just narrate here. What we're doing is we're looking at 2 point on wave time series that are coming in. And what's going to happen is the sensor manufacturer, the sensor group is going to start introducing anomalies into the waveform. So they're gonna glitch the waveform. They're gonna do power outages. They're gonna do over voltages, et cetera, et cetera. And what's gonna happen is we're detecting this in real time, and then we're emailing over to the person specified. And once we've detected it, and the detection's almost instantaneous. You can't hear that on the audio. But now what we're doing is we're zooming in through, and this is a 10 kilohertz wave, zooming into the specific event to identify it. And yep, there it is, just as we saw. And we're going through and we're detecting in real time these different signatures in 10 kilohertz signals. And this is an exciting project because imagine what one could do if you went from AMI data at, sampled once every 15 minutes to 10 kilohertz. So with no further ado, those are the 2 demos. I'm gonna stop that and go to the next. So Chris, at this point, I'm gonna turn it over to you and we're gonna swap screens. So I'm gonna stop sharing for a moment.
Sure. Thanks, Sean. Let me just queue it up. All right, so I will presume that I'm sharing my screen. If anyone can see it, just shout out.
We can see it, but it might be better in presenter mode.
Yeah. Okay, great. Thanks so much. Thanks everybody, and thanks Sean for the intro. So Sean mentioned I'm a data scientist at PingThings, and I was the project lead on our end for this collaboration with Emran. I will go over some of the technical details of the project as it was executed. So a large, an overarching theme of the project was, can we quickly develop machine learning and AI-powered analyses on Emran smart meter data sets? So the hypothesis is that there's a lot of useful information in time series that are recorded by smart meters. What does it feel like to quickly, rapidly test these things and see what's useful, what gives useful results, and what's actionable? So the size of a typical analysis is that, for example, if one was interested in analyzing all the meters associated with a particular substation, that can be up to thousands of meters. Some of them are much smaller, but a typical large substation would relate to thousands of smart meters. And can we analyze up to a full year worth of data for each meter when we analyze it all together? And so somewhat separate from this question of, can we do machine learning and get sensible results, is can we make useful predictions about the state of the grid? What is actionable and what brings value to Emran and potentially other kinds of power utilities with similar interests? You might be interested in wondering which smart meters are incorrectly mapped to transformers, by which I mean, if there's an internal mapping that is curated by hand internal to Emran or internal to a power utility, how accurate is it? In an ever-changing grid, you might want to check to see, can we update it and can we correct the mappings that we have? And similarly, you might want to check what voltage phase any particular meter is on. even if you have a similar internal mapping, things change, and you can use data to back out what voltage phase a certain points might be on by comparing it to a known time series, for example, that would that has a voltage phase you know about. So the approach here is to test 3 different algorithms, each with increasing sophistication. You might consider kind of an accuracy versus efficiency trade-off as you employ more accurate algorithms. It's going to often take more time to compute. So what does that feel like, and what do the results look like? So I'll say a bit more first about the source data set. Sean already spoke a bit about this, but it consisted of 8 terabytes that we received on our end of compressed CSVs from Emrin through EPRI. It was very helpful during this time, during this process. 8 terabytes of compressed CSVs of source data was transferred to our platform, and then we loaded that into the platform. Well, were transferred to us, and then we loaded it into the platform. And within this data set, it consisted of about 1 million smart meters, and the readings that they were recording over 12 months during 2019 and 2020. Each smart meter was sampling every 15 minutes, roughly. Some of them weren't, but in general, they were all sampling at 15-minute intervals, and they each had 3 measurements. One was voltage, one was apparent power, and one was real current. So 3 streams per meter and 1 million meters means 3 million time series. So the first algorithm we tested is one of the most basic ways in statistics to test similarity between 2 data points. If you're familiar, if you have a background in statistics, this is the Pearson Correlation. And just to add a few technical details for those familiar with this, the first step is to calculate the covariance. So to take 2 voltage time series, for example, calculate the covariance between those 2 series. So in other words, this is a measurement that says, when one series goes up, if the other one goes up, they have a higher covariance. If one series goes down when the other one goes up, they could have a negative covariance. So looking across the entire time series for that and computing kind of a hard statistic for it. And the second step is to normalize that to a number between -1 and positive, -1 and +1. So a Pearson correlation of exactly 1 means that all the values were exactly the same. -1 would mean that between these 2 meters, one was always up when the other one was down, and they're basically anti-correlated in other words. But details aside, this is a kind of a similarity metric between 2 meters. Similarity metrics are useful if you're trying to infer organization in the grid, because then you can see, if these 2 meters are highly correlated, they're probably next to each other in the grid. If they're very anti-correlated or they're uncorrelated, they may be far away. We tested on our platform both a fast version and an exact version of this calculation. The fast version is approximate, and it takes advantage of just if you load all the data into a 2-dimensional array in memory, you can all at once compute these correlations between all meters, which is a good approach and is very fast. And does require some approximation. If you want an exact version that's a bit more accurate, you would do a calculation between each meter pair. And that's more expensive, but on our platform, it's still very doable. It takes on the orders of tens of minutes instead of seconds, which we'll see in a bit. In fact, we'll see it right now. So I will link off to a live demo. And I believe you can all see the screen. If you can't, just let me know. So this is just a quick demo of what it's like to use the platform and for developing Python data analytics code. So Python is a language that has a very robust data analysis and data science stack. So I'll just be walking through at a high level the code for an actual analysis. So the first step is that you load your libraries, the kind of tools you want to have at hand for your analysis. I also have some helper files for Emrin's specific data set that helps me map the platform's description of the data to things like meter IDs. And then I'll load the data. So what I'm doing here is loading an entire data set for one substation. So you can see this is it in these 4 seconds that I just ran in this code. It loaded every value for 679 voltage series for 679 smart meters, ones that are associated with one substation. The cell below it, in a year, and you're sampling every 15 minutes, that's about 38,000 points for each of these 679 smart meters. So in that 4 seconds, loaded all the raw data, for all these things, and align that into a 2-dimensional array. And so after doing that, I will compute the correlation. So for this demo, I'm just doing the approximate approach. This environment, as Sean mentioned, is co-located with the database. So not only was the loading fast because it was retrieved in a location that's next to our database, but it's in a high-performance compute environment. So when I execute the analytics for that entire substation, for those 38,000 points for 680 meters, that took 1.2 seconds. And this is what the results look like. So I mentioned it's a Pearson correlation. You're going to get values of 1 if they're exactly correlated. So there's a diagonal of 1 because every meter is correlated with itself. And then you get a value for every meter pair in this matrix that pops out of this Pearson correlation analysis. So for example, you see that meter, these are anonymized meter IDs, by the way, but the Pearson correlation for the anonymized meter, 512532 is very highly correlated with the anonymous meter 965202, and so you can infer that they're probably very closely related and close to in space to each other on the grid. Rather than examining that in a big table, you may want to make plots, and Python provides a great ecosystem for creating useful plots. This is exactly the same information as the table I just showed, although it's actually a subset because showing, a 679 by 679 square would be kind of a lot. So I'm only grabbing, how much am I grabbing? 50 by 50 chunk of that table I just showed, but I'm using colors instead of numbers to show the information. And it's lighter if they're more highly correlated and darker if they're not very correlated at all. I'll speak about this more in a bit, but one of the outputs, if you have scores like this, a number for every meter pair, is that you can use that to infer the hierarchical organization in the grid. So I'm just going to execute this function, which is just for plotting the results I'm going to calculate in a moment. And this should take about 20 seconds. But what it's going to do is it's going to receive as an input the data that I just showed, which is 1 score for every meter pair, and then iteratively produce what would be called a hierarchical clustering. So kind of you can see groups of meters and how they're co-located together. And the results are here, and it's a ton of information. So I'll zoom down really fast. What has happened here is that the result of this calculation is this kind of a tree. I'll describe the colors in a moment. But if the legs that join any 2 of these anonymized meters are short, that means they're close together. And then you see that there's a hierarchical grouping that comes out of that as well. The colors correspond to transformer IDs that Amrin has. So the colors are separate from the analysis that I just did. This is Amrin's internal mapping, again anonymized, of meters. And you can see that this big chunk of purple-ish meters are clustered very closely together. You see all these short legs. That's a good sanity check because That's a sensible result if you are doing an analysis that's supposed to look in the data for groupings that actually matches the groupings that we think are true. And then in addition, as I mentioned earlier, you can use this as a basis for kind of guessing and prioritizing which meters might be mismapped. If you find a meter that is in a different group than you expect it to be, you may want to go hand check, and maybe that one's incorrectly mapped in your internal mapping. And that's the full live demo. I'll hop back to the slides now. And also, I am covering the other algorithms in less depth, so I'll go a bit faster now. So you see, this is just an example of the plot I showed earlier. This is a comprehensive benchmark. So in the previous example, I showed a substation that had about 700 meters associated with it. Some of the substations have thousands. So what does that look like on the platform? For loading data, that's the left plot. And so you can see as before, if it's about 800, that'll be, it can vary from, ones of seconds to up to 10 seconds, maybe 20 seconds. If you have a substation that has 4,000 smart meters, you might need 2 minutes to load the data, but that's still quite rapid for loading, again, 38,000 points for 4,000 meters is a ton. And then on the right, you see an analytics benchmark. So that calculation that I believe took 1.2 something seconds for that 800 meter substation. What does that look like on larger substations? And it scales quite nicely as well. If you were, one of the much larger substations at 4,000, that would take 14 seconds. So still quite doable. We tested 2 more algorithms very briefly. I'll describe them. So the second one is a bit more sophisticated of a machine learning approach. This one uses network theory as a basis for the approach. And that's important because the grid is a network. And so machine learning algorithms that are based in this way there can be kind of a natural fit in the patterns that it finds if you're using that as kind of an ingredient to your analysis. Spectral clustering uses network theory and then some linear algebra transforms to sort of simplify the representation of the data. So you're not working with this 4,000 by 40,000 matrix. And then it uses another machine learning step to discover groups within that simplified representation. And the figure on the right, I don't have, going into it deeply is beyond the scope of this talk, but it's basically a kind of a scoring of that result, real scoring of that result from an analysis we were doing. And you'll see that for each of these spikes toward the right, they're all positive. So this is the result of a kind of scoring that tests the quality of the groups that you're finding. And if they're positive, that's good. And we found a bunch of positive scores when we used this approach to find groups in the data. Along the way, you also get another similarity metric from this approach. Similar to the Pearson correlation, you would get like another score that's between pairs of meters. And that's useful because then you can start to evaluate each approach on equal footing, especially if you have I showed the example before where that can be an input to that tree that I showed. You can use the spectral clustering result as also an input to that tree, and then evaluate, if you have a process of using these results, evaluate them on equal footing. This was a published paper fairly recently that we applied to Amron's dataset. And then similarly, there was another published paper. This is the third and final algorithm called BottomUp Grouping. So this one is interesting because it uses all the time series data we have available in this data set. So power data, voltage data, and current data as a basis for the algorithm. And then it inputs that into the physical equations of electricity. And then it also uses linear regression with the data to back out some results. Some of them include things like reactances along the grid. So physical properties of the grid, because we're using physical equations. another result is that we get yet another similarity metric between each meter pair. So another score between 0 and 1. This one's called R squared. It's the one associated with linear regression. On the right is another plot that I don't have the time to go into too deeply, but the takeaway here is that in these, you see a orange distribution and a blue distribution. The blue distribution, which contains voltage, power, and current data, shifted a bit to the right. That's an indicator that including this data is actually quite useful in giving better results than if you just had the voltage data only, which is the orange distribution. And with that, I will just summarize some takeaways. The PingThings platform for this work provided a high performance compute resources that are co-located with a blazingly fast time series database and really accelerated a lot of the work. It really enabled the rapid prototyping and assessment of these 3 different machine learning algorithms for smart meter data. And then an outcome of each of these algorithms with a similarity metric that can all be evaluated on equal footing for their accuracy, actionability, and efficiency. And that's all I have to show. Thanks to you all for your attention, for showing these technical details, as well as everyone and Amran and Empery that helped bring the project to fruition. And please reach out to me if you have any questions at all or would just like to connect.
Thanks, Chris.
You're welcome. Thanks, everybody.
Okay, let's see. Oh, once you stop sharing, I can jump on. I can jump back in. Okay, so just to wrap this up, in terms of experiences, Amran focused on doing similar work on AWS with AWS components, and initially prototyping the algorithms on laptops with very small data sets, and then trying to get those algorithms operational within the various options available, such as EMR, Elastic MapReduce, and Spark, where PingThings focused on getting those different algorithms up and running, tested on our platform, and then scaling them out. So we kind of parallel tracks to accomplish the same thing. I think Amran ran into some limitations on some of the functionality offered by Spark. So if Spark didn't have a pre-built function to get something done, it was somewhat of a blocker. So just as a note, in terms of, Scott, did you want to jump in and say anything, or?
Yeah, Ed, happy to jump in there. Let me turn my camera on here. Yeah, that's an excellent point, Sean. That was a bit of frustration on our side. If anyone's familiar in working with big data, Spark's like the go-to. It's been around a while. It's most well known. If you look at people productionalizing big data applications, they're using Spark. But what we kept bumping up against is that while Spark's been around a long time, the built-in functionality that it has isn't that great, and the ability to build custom algorithms within it isn't that great as well. So it forced us to really bob and weave a little bit, kind of when we're trying to figure out, okay, well, instead of just tackling the problem exactly how we would want to tackle it from a mathematical perspective, we really have to see what's available in Spark. Okay, well, how can we take that, maybe flip it, adjust it, and then manipulate that to meet our need? Where one of the things we were really impressed by was with your team's Ray implementation was you guys wrote your code in Ray exactly how you'd like it, and you were able to deploy it at scale on a big set of data exactly how you'd want it. Yeah, I'll kick it back to you, Sean, for keeping it going.
Yeah, absolutely, and appreciate the commentary and the perspective. It's really helpful because I know there are a lot of utilities that are evaluating experiences and how to do these things, and there are a ton of options. Getting to the benchmarks that we ran, where it was a subset, so 64 substations, not all of them, where we're performing voltage correlations. And on the left are the results using AWS and Elastic MapReduce with S3. And then on the right, PingThings and the predictive grid. And the sequence of steps was very similar. They're loading data files, optimized binary data files from S3 in the EMR. This should be lightning fast given S3's enormous bandwidth. And then Elastic MapReduce is performing all of the data transformations and the calculations. And then the sequence of steps over for PingThings is very similar. We're reading data from the platform, so our database, and then we're actually doing everything in a Jupyter notebook in Python, transforming data and the calculations. So the interesting thing is order of magnitude, the total time to compute, 60 minutes on the left, 35, 45 minutes on the right. But the thing that I want you to take note is that for Amazon's about throwing horsepower. So in the EMR cluster, there's 8 extra large instances. And those extra large instances are actually a pretty recent CPU with 8 virtual CPUs, lots of memory, and just a really like 10 gigabit per second network, which is nice. And our numbers actually, we were running for the benchmarking, we actually were running single core in Python, in a single Python process. And we were using, I hate to say this, but we were using a pretty ancient 2010 Xeon processor. Startup, we have a co-located facility. We bought the servers. They're very old. They were secondhand. We've had them forever. Don't judge me by the hardware. And they only had 8 gigabytes of RAM. So we were able to do sort of same order of magnitude, slightly faster, with literally 64 times less computing resources. So I think that shows you, if we scaled to that sort of beast of a cluster, I mean, this thing would have flown. We would have finished much faster, but like we have a very efficient, very fast platform, which has been optimized for working with time series. So just, I love these results. They're great. I know the Amarin team was a bit frustrated with some of the limitations on the software side for Amazon. And this was a good solution from them. Like this is the way you would do things. And so in terms of the conclusion, we found that, hey, look, our platform is good, and we wanted to demonstrate that with AMI data, right? This is data that's sampled once every 15 minutes. We're used to working with hundreds of thousands of 30 sample per second data streams. We're working with point on wave, we're working with PMUs. How well would we do with much slower data? Even though, now there's millions or tens of millions of streams, turns out we do quite well. We're really good across the spectrum of sample rates with our platform. And the beautiful thing was working with Amarin and understanding what they're thinking about and the problems they face really gave us insight to help improve different things that we're working on, like our next generation query engine and our next generation API. And it was a great, the overall experience was great. And we hope in the future, we'll be able to work further with Amarin and expand and bring synchrophaser data in with AMI data if they so choose. So at this point, I will wrap things up with 10 minutes to spare and open the floor up for questions.
Hey, that was great, Scott, and team. Thank you so much. I do know that there were a couple of questions that have come in that Ed's been tackling with us. I wanted to, I guess, JVC7 is asking a little bit more about what about live data and predictive streams such as meter topology and outages and equipment failures.
Oh, good question. So we handle streaming live data just as well, if not better than like big ETL uploads. The platform was really designed to initially to receive streaming data from synchrophasers at first, but we can accept pretty much any type of streaming data, and we can run. A lot of times the analytic development work is done asynchronously, but we can run analytics in real time as well if that's desired. So we're pretty flexible with how we operate and what type of capabilities we expose.
I'm going to ask a question as well. And this one is really directed at Scott and Ameren. Coming out of this project, what's next? What's next for Ameren, and what did this teach you about how you want to work with AMI time series data moving forward?
Yeah, good question, Annie. So this was very much a stretch project for us. Something that Sean kind of hit upon when he showed the timeline plot is that we executed these projects on very, very, very short timelines. So that's something important to keep in mind, but it was also a stretch for us from a technology perspective. So when we did these things for the first time in AWS, these were some of the items that we had roadmapped in, well, we're going to throw our AMI meter data in S3, and then we'll be able to work with it. And I think one of the important things that we've learned here is that being able to get and access that data quickly and efficiently is tremendously valuable. So Sean, could you go back to that benchmarking slide?
Yep.
Yeah, so I mean, what you're seeing here is you can see the times on the bottom and the drastically lower resources that the PingThings platform used. But something that isn't even included in this that Ameren had to do prior to even getting to this stage is that as we were data scientists working on this project, you need to get your data in a format as you need it in order to be able to feed it into your algorithm. And upstream of this was an additional 4 hours of processing to get that data in the exact format that we wanted. So that's not even included in this. And why I'm bringing that up is that something that was very illuminating in this project is that as you're working on analytics projects, and whether you're at the development, testing, or implementation phase, it's very important to be able to get your data in and out as quickly and efficiently as possible, and also have flexibility on how you want to view it. So that was the most illuminating thing in that from this project. And right now, Ameren is working on our sensor data strategy and all of the items that we've learned from doing this project about the complexities of working with time series data, especially data of this volume. We're going to be baking that into our sensor data analytics strategy and making sure that as we build out our infrastructure, that we take the learnings from this project and incorporate that. I mean, it was tremendously eye-opening. This was really a stretch project for Ameren and what we were able to do with such large amounts of data in AWS for the first time.
Yeah, thanks for that. And I remember that initial data, discussion. Ed, I see you've got your camera on, and like to ask you the same question. Coming out of this project, what were some of your sort of key outtakes and overall impressions?
Yeah, well, one of the things is just what Scott was talking about. Is the process of actually getting the data from wherever it happens to live. And in some cases, it's multiple locations, right? So there might be topological data, showing how your network is actually constructed. There might be AMI data. They might not be on the same platform. Those two platforms might not even communicate with each other. So just wrangling the data and assuring that it's ingestible in any form is a neat trick. And it takes a lot of time and effort and thought in doing it and doing it efficiently. The other thing I think is probably worthwhile mentioning is that in this particular case, we actually had 3 entities involved. So there's EPRI, Ameren, and PingThings. And so don't underestimate the ability of lawyers to slow things down as well. So one of the initial hurdles when we all wanted to make sure that this actually needs to, we need to respect the privacy of the individuals whose data this reflects. We also need to make sure that we have proper data governance at each stage of the process, so that the data is encrypted when it's transferred, that it's safe at rest. We need to have a lot of controls built in to make sure that the data is only revealed to those who actually need to have access to it and not revealed to anyone else. In addition, we need to make sure that it's actually available to the authorized folks. So all of those things, there's a technical aspect, but there's also an organizational, social, legal aspect to things that I think is, especially if you're going to be working with a third party, definitely something that needs consideration up front, and give the lawyers a lot of lead time. The only other thing I'll mention is that one of the things I was intrigued by and impressed with this whole process is that rather than being something of a blank canvas as AWS is, or a canned data analytics package where you just feed it data and it automatically comes out with answers at the other end. This is neither a blank canvas nor some opaque black box processing tool that you use. So the real advantage is that it actually helps you develop the algorithms using your data, apply those algorithms without either requiring you to invent everything from scratch or without chaining you to a particular solution that you can't alter, tweak, or even look at in some cases. So very interesting. I would like to see more of these kinds of products in the future.
Excellent, thanks. And we now know who JVC7 is, so thanks, Jesse. Jesse had another question about transforming the data. Did you use brute force or did you use a platform such as Outtakes?
So we did all the data transformations actually within a PySpark cluster, and we had some highly performant code to do that. So even with really performant code, essentially written in PySpark, it still took 4 hours to do those transformations just because the data volume was so large. So it was PySpark with an EMR cluster. That's how we did it.
Okay, thanks for that.
And that's reading and writing from Parquet files to Parquet files. I think there was another question about location data tied to those sensors. So we did have some GPS data associated with each one of those sensors, and the sensors were AMI meters. So that was available, and so this was an unsupervised learning approach that we took. So what that means is with regard to how did we check stuff? So we took an unsupervised approach, but we did know and did have some field investigations that we did use to tune these models. So we took a largely unsupervised approach, and then we did have some ground truth or some field investigations and knowledge about where things are in the grid in order to be able to tune these algorithms for that final step of transitioning to a more supervised approach. If that answers your question, Donovan.
All right, thank you. Well, we are actually at the top of the hour. I want to say thank you to everybody. If you would like to get in touch with PingThings or the folks on this project, go ahead and shoot me an email. Put my email here in the chat, and feel free to send me a message, and I'll make the connections here. So thank you all for joining us. Team Ameren, thank you a million. Team PingThings, thank you so much. And of course, thanks to all of our folks behind the scenes, and Ed, our very special subject matter expert at EPRI, who's been helping guide this along the way. So with that, we bid you farewell and a great weekend. Thanks, everybody.
Thanks, everybody.
Thanks.
Thank you. And
Thank you.
anybody feel free to reach out if they have questions. Thanks.